Part 2, this is for questions 11 to 20. Question 11, an experiment is carried out to determine the value of X in hydrated lithium hydroxide. A sample of the solid is heated in a crucible over a Bunsen flame. Complete dehydration takes place. Decomposition does not occur. So when you said complete dehydration takes place, that means all the water has been evaporated. Okay. Then they are saying mass of empty crucible is equal to this. And then also when they say decomposition does not occur, that means this lithium hydroxide, after losing the water when you heat, this one doesn't decompose, okay? It remains as lithium hydroxide. Then mass of the crucible with lithium, with hydrated lithium hydroxide is R. So you put the crucible on the weighing scale, and then you get the mass of the crucible, okay? Then after you pour this solid here, then you see again the mass. That means you are going to get the mass of lithium hydroxide, the hydrated one. It will be R minus Q. Are we there? Then mass of the crucible and residue after heating. So you get your crucible here, you put it on water. You put it on what? On the Bunsen flame. And when you put it on the Bunsen flame, it is going to heat up and then water will disappear. That means what you will remain with here, it is going to be lithium hydroxide here and the crucible. So that means we need to get the mass of lithium hydroxide. So mass of lithium hydroxide is going to be, first of all, there is mass of the empty crucible there. So if this is the total after heating, then I'll have that S, then minus the mass of the empty crucible. You see that? So I'll be remaining with this solid only. You see that? Then we also need now to find the moles. To find the moles of this one here, I will then, I'll need the MR, okay? The relative formula mass of this one. So the MR of lithium hydroxide is going to be, what is lithium? The AR of lithium. Let's check the periodic table. So when you come to the periodic table, lithium is here. So the AR is 6.9. 6.9. Then plus oxygen is 16. Then plus hydrogen is what? Is 1. So this is 17 plus 6. That is 23. Then 0.9. So we have 23.9. Okay. So that means moles of lithium hydroxide. This one is going to be the S minus Q, which is the mass, then divide by this MR. Okay, I keep that. Then I go to water. What is the mass of water? Mass of water of crystallization in here, it is going to be, remember, mass of the crucible with that water there in the solid is this. Then after heating, you are having this. So water has disappeared. That means you will have the mass of water as R minus S. Don't you see that? So we shall have R minus S. And then after that, we shall also find moles of water. The MR of water is going to be 16, then plus the 2 here, that is 18. So we shall have R minus S, that is the mass, then out of the MR of water, which is what? 18. Now I will have lithium hydroxide here. When you're finding the value of X here, you use this method as if you're calculating what we call the empirical formula of a compound. So you put lithium hydroxide here, and then you also put what? Water here. Then you get what we call the mole ratio. Okay, so first of all, the moles are, for lithium hydroxide, we have S minus Q, then out of 23.9. Then for water, we have R minus S out of what? 18. Now, when we are finding a value of X here, of course, since we are having moles of water, okay, in most cases, this X is greater than 1. That means the moles of the hydroxide here, the number of moles of the hydroxide is smaller than the number of moles of this. So we divide all through by the moles of this hydroxide here. So I will divide all through by S minus Q out of 23.9, then out of the same thing, S minus Q out of 23.9. Now here you will get a 1, okay? Just like you have 1 mole of this one here, then 2. How many moles of water? You see that? Then this one here will be X. So we have something like 1, 2, then the X here. So our X is going to be the whole of this one here. I can simplify it like this. R, then minus X, minus S out of 18, then times the reciprocal of this denominator using rules of fractions. So 23.9, then out of S minus Q. That is what we are going to get here. And if you check our options, we see it as what? As C. 23.9 multiplies with the R minus S, as you're seeing here, then 18 with the S minus Q. So that is that. Question 12. A sample of an ideal gas occupies 240 cubic centimeters at 37 degrees C and 100 kilopascals. How many moles of the gas are present in the sample? For any ideal gas, we use PV is equal to N, then RT. Now, P has to be in pascals or in Newton per meter squared. Why in Newton per meter squared? Because we know pressure is equal to force over area. And the SI unit of force is newtons. The SI unit of area is meters squared. So that's why we are saying Newton per meter squared. Okay. And then after that, since the area here is in meters squared, that means the volume has to be in meters cubed. Okay. But now here it is in centimeters cubed. So what do? We know that 100 centimeters, it is equivalent to 1 meter. Now we need cubic centimeters, so I'm going to cube everywhere. So this one cubed, then we shall get 1 meter cubed. Remember, volume has to be in what? Meters cubed. So this simply implies that 1 centimeter square, cubed, is equal to 1 over 100 cubed. This is the same as 10 squared, then power 3, then this one will multiply, then we shall have 10 to the power of what? 6. So we shall divide it here, okay, like that, which is actually the same thing as saying 10 to the power of negative 6, then meters cubed. So that means if we are given the centimeters cubed here, we shall replace this one with 10 power negative 6 meters cubed. You see that? So we are looking for the number of moles. So making N here the subject of the formula, it will be PV, then out of RT. So our pressure is 100,000 pascals, then times the volume, which is 240, but we shall multiply it with 10 to the power of negative 6. It has to be in what? Meters cubed. And we have already converted that, okay? Then after that, we divide by R, which is 8.31, the molar gas constant, then times the temperature, which has to be in kelvins, okay? Temperature has to be in kelvins. So if it is in degrees here, then we shall add 273, okay? Now, when we put this one in the calculator, what do we get? We have 100,000, then times, we have 240, then times 10, then to the power of negative 6. We go down, we have 8.31, then times, we have a 37 added to 273. And that one gives us 80 over 8587, but in decimal places, we can have to 3 significant figures, 9.32 times 10 to the power negative 3. 9.32 times 10 to the power negative 3. And when we look at all our answers here, it has to be a B. Question 13. Under certain conditions, carbon tetrachloride and water react as shown. The activation energy for the reaction is positive 62 kilojoules per mole. And this is the reaction here. And we are seeing that the enthalpy of reaction is negative. So the reaction is exothermic. So if it is exothermic, that means energy is given to the surrounding. So what is remaining as the products, then we are going to have them at a lower energy. So we have to look for diagrams like these ones here, where the products have gotten less energy compared to the reactants. Okay, that one there and this one here. So this one is endothermic, because for endothermic you put in energy. That means the products are going to have much more energy compared to the reactants, because energy has been absorbed. You get that? So this one is off and this one is off. You see? Now they give us the activation energy. So we look at this part here. Okay, that one there. And remember, activation energy is the minimum amount of energy these reactants must possess in order to react. See that? Now, if this is 62, okay, and this one here, leave alone the negative, this is 61.5, they are relatively the same. But when you look at A here, from here to here, you're having something like this. Then from here to here, you can see that this one is far bigger than this. Okay, so that means this one cannot be our answer. So the answer has to be what? A D. Because when you actually look at these ones here, when you try to look at this activation energy and then this one here, they are relatively the same, you see, in magnitude. So this one is negative 61.5 kilojoules, and then this one is positive what? 62 kilojoules. Question 14. A helium ion contains 2 protons, 2 neutrons, and 1 electron. Now, helium is in position 2, so it has 2 protons, and they are saying 2 what? Neutrons. That is the nucleus. But let me make it a little bit smaller. 2 protons, and then 2 neutrons. That is the nucleus. Then we have the first shell, which has the 2. It is supposed to have 2 electrons, okay, because it is in position 2, but it has lost an electron, so we are seeing 1 electron. So this helium here is positively charged because it has lost 1 electron. So there is a proton here that doesn't have a counter electron in the orbit here. You see that? So it remains positively charged. Then they are saying this helium ion and the proton are passed separately through a uniform electric field. Now, particles are traveling at the same velocity, which rho describes the path of each particle. And when I look at the options here, we are supposed to focus on the helium ion and then the proton. Now, when we look at this one here, the helium has an ion. Its mass is 4, okay? Because a proton has a relative mass of 1 and also the neutron. So there are 4 of them in the nucleus. So we shall have 4, okay? 4 units there. And then when we look at what else? We look at a proton. So protons, we have 2 protons in here. That means the mass is going to be 2, okay? 2 times the 1, that will be 2. So meaning the helium ion is heavier than the proton. So when we come to deflections in here, first of all, these 2, they are all positively charged, okay? So if they are positively charged, then they will be deflected towards the negative one plate. So after being deflected towards the negative plate, now the angle of deflection here matters based on the mass. So we call it the mass to charge ratio. The mass here is bigger. That means the deflection is going to be smaller than for this one here for the proton. So this 4 here, the deflection here is smaller. The angle here is less than this angle here for 5. Okay, so that alpha is bigger than the theta that I've put there. So meaning this one for the smaller deflection, it has to be for the heavier particle. And the heavier particle is this helium ion. So helium ion, we look for a 4, which is here. And then the proton will take on this 5 because it is smaller. Then there will be a bigger deflection. So it has to be here. And therefore our answer becomes a C. Question 15. The skeletal formulae of arginine and lysine are shown. So this is the one for arginine and then the lysine here. Which row is correct? And looking through the options, They want us to find the empirical formula and then the molecular formula. So let's go to the one of arginine. Here there is a carbon. Now, for what we call the skeletal formulae, they don't show you the carbons and also the hydrogens that are directly attached to the carbon. They are showing here the hydrogens that are connected to these. These are functional groups. So they are connected to the nitrogen here and then the oxygen. These hydrogens are shown. But the ones that are directly connected to the carbon, they are hidden. So here we have CH2. Remember, carbon has 4 bonds. So these are already 2, then 3, then 4. So we don't have a hydrogen here. You see that? So we shall have that, then a carbon here, then other 2 hydrogens. The same here, we shall have a CH2. Then here there is a carbon. Now these are 3 bonds, so we must have a hydrogen. And then a carbon here. These are 2, 3, and then 4. So that is that. Now, what is the molecular formula? The molecular formula here is going to be, how many carbons are we seeing? 1, 2, 3, 4, 5, 6. Those are 6 what? Carbons. So if we are having 6 carbons here, what about hydrogens? So hydrogens, 1 here, then plus the 2, that is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, then 14. You see that? So those are 14 hydrogens. Then how about nitrogens? We have 1, 2, 3, and then 4. Okay, 4 nitrogens. Then oxygens, we have 1 and then 2. So that means empirical formula is going to be, empirical formula shows the simplest whole number ratio of the atoms present in that given what? Molecule. But then the molecular formula shows the exact number of atoms present in that given what? Molecule. So I can divide all through these numbers by 2. Then you get C3, then H what? H, then 7, and then nitrogen in here 3, and then oxygen 1. So what will be the MR of this one here? Okay, the MR is going to be 6 times 12. Then we have 14 times 1 for hydrogen, and then 4 times 14 for nitrogen, and then oxygen we have 2 times the 16. So this one will give us 6 times 12, that is 72, then plus a 14, then plus 4 times 14, which is actually 56, then plus 2 times 16, which is 32. So adding everything together, this is 174. Now let's look at arginine. Arginine, the empirical formula is this one here. So which one do you think? C3H7N2O. This one is correct. Then the molecular formula, we have seen it is 74. So these two are correct. So that even means our answer is supposed to be A. But let's look at lysine. Okay, there is C, then hydrogens, 2 of them. Also here, here, then also here, 2 of them, like that. Then there is a carbon here. These are 3 bonds, so we must have hydrogen. Then there is a carbon there. So how many? Let us look at the molecular formula. The molecular formula here is carbon. How many are they? 1, 2, 3, 4, 5, 6. So those are 6 carbons. I'll put a 6 here. Then hydrogens, how many are they? These are 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, then 12, then 13, 14. So we are seeing 14 what? Hydrogens here. Then nitrogens, how many are they? 1, 2. And then oxygens are also 2. Then that means the empirical formula is going to be divide all through by 2. You have C3, then H7, and then N, and then also O, something like that. Don't you think it is this one here? That one is correct. But let us look at the what? The molecular formula, the molecular mass. Relative molecular mass, 6 times 12, that is a 72. Then plus 14 times 1, then plus 2 times 14, then plus 2 times 16. So altogether, what does this one give us? Remember, when we are finding the relative molecular mass, we use the molecular formula. We don't use empirical, okay? Remember, 6 times 12 is what? 72. Yes, we have 72. Then plus 14, plus 2 into 14. Then plus 2 times 16. That one gives us 146. 146. But here they are giving us 144. You see that? Then when we come to this one is a wrong empirical formula, yet the molecular formula is correct. So that means our answer is A. Question 16. The oxide and chloride of an element X are separately mixed with water. The two resulting solutions have the same effect on litmus. What could be element X? Now, when you look at this is a group 2 element, this is a group 1 element. When you look at the oxide of calcium and you mix it with water, you'll get a hydroxide. Then the effect on the litmus, if it is red litmus, it will turn blue, okay? Because that one is an alkaline solution. Then the chloride of this one, when you add this calcium chloride, when you add it in water and you put the litmus paper, it is going to cause no change. This one is a neutral hydroxide. Is a neutral solution. You see that? So calcium has to be off. Okay. Then we go to sodium. Sodium is going to do the same. Sodium oxide, then you add it in water, you get sodium hydroxide, you put red litmus, it turns blue. But sodium chloride has no effect on the what? On the litmus. Okay. So that is off. Then we are supposed to look at aluminium and then what? Phosphorus. Then you are saying the oxide of later aluminium. This is aluminium oxide mixed with water. This one is insoluble in water. That is why we have the overhead power cables made of aluminium. So the aluminium reacts with the oxygen to form this aluminium oxide, and then this layer covers the wire, and then from there, even when it rains, this layer protects the aluminium from further reaction. So this one does not react. So that means when you add blue litmus, it is not going to turn, or red litmus, nothing is going to happen here. Okay. Then the chloride of aluminium, this aluminium chloride, actually, we can have a dimer. Okay. This one here, but in the presence of water, this one is broken down. And then we have aluminium in solution. So this aluminium ion is going to be surrounded by water molecules. They are actually 6 of them. So we have aluminium, this one here. Okay. 6 of them. It forms like a complex. Then this complex here is able to, because aluminium is small and has gotten a very high charge, so it has a high charge density. So it is able to cause a molecule of water here, okay, to lose a hydrogen. Remember, this one is partially negative because it tends to pull the bonding electrons towards itself. It is electronegative. Then these hydrogens tend to lose the electrons. So this strong attraction in here makes one of the hydrogens to be lost. So in doing so, you will find that aluminium with water here, then this one here, when you put it in water, you are going to have, no, actually, let me just pull off this. What is going to happen is that one of the water molecules, there is something wrong here. There is not supposed to be a 2 here. Okay. Now, one of the water molecules is going to lose an OH, a hydrogen. That means these ones, which were 6, are going to remain 5. And then here, since this one has lost a hydrogen, there is an OH here. So this OH attaches itself here. You see that? And then because its charge is -1, then it is going to reduce the charge here. Okay, 3 minus 1, you get a 2. That means I'm going to have a positive 2 here, okay? Positive 2 here, then plus the hydrogen ion that has been lost. This process continues until you have aluminium here, when it has 3 water molecules have lost the what? The hydrogen ions. And then this charge is completely gone. So you will have 3 water molecules here and then the 3 OHs. Then here we don't have any charge because 3 OHs which are having the negative charge, and then the 3 plus, it will go. You see that? So this one I will even write it like that, and then you have 3, this one here. So that is why when you get a chloride of aluminium and you dissolve it in water, you come out with an acidic solution because of the production of what? Hydrogen ions. So that means when you put blue litmus paper, you're going to get red. I mean, the blue litmus paper is going to turn out to be red because of the acid. Are we there? But then the aluminium oxide, when we added it in water, we got nothing. Okay? Because aluminium oxide does not dissolve in what? In water. But yet here they said the resulting solutions have the same effect on what? On litmus. So that means aluminium is also off. So our answer has to be what? D. But then what do we see in D here? You are going to have phosphorus. The chloride, the oxide of phosphorus is going to be this one here, for phosphorus pentaoxide, but it dimerizes. So we have this one here. Then when we add water, we are going to form phosphoric acid. Okay, this is its formula here. And then when we try to balance, phosphorus is 4 this side. So we shall multiply this way by a 4. I will put a 4 here. Hydrogen now becomes 12. So that means I will put a 6 here. Then oxygen is 6. Then plus the 10, that will be 16. You have a 4 times the 4, that is 16. So this one is an acid, so it will turn blue litmus red. Then we also go to phosphorus pentachloride because they say the chloride of an X. Okay. Then when we add water, there is hydrolysis reaction that takes place here. So you will get again phosphoric acid, then plus HCl. These are white fumes, the steamy fumes that come off. And then chlorine, there are 5 here, so I'll put a 5 here. And then what else? So what do we have? Hydrogens are 5 here, then plus the 3, there will be 8, not so? Coming this side to make 8, I will put a 4 here. And then oxygen is 4, and then 4 here. So that one is balanced that way. So even this one is acidic already. This is an acid, and this one is also acidic. You see that? So again, when you dip blue litmus paper here, you get red. And also here, it will turn red. So same result. That is why our answer is what? Is D. Then question 17. Why do halogens become less volatile as group 7, as group 17 is descended? So this one is actually about the number of electrons. Okay, as you go down the group, the number of electrons increases. And when the number of electrons increases, that means the strength of van der Waals forces that are holding these molecules together will increase. So that is why you find that iodine at room temperature, it is a solid because of the stronger van der Waals forces. Then bromine, which is higher than chlorine, for it is a liquid. And then chlorine, which is higher than bromine in the group, for it exists as a gas, and also fluorine is a gas. Why? For them, they have very, very little number of what? Electrons. So they have a very small number of what? Electrons. Okay, let me actually show you in the book. So when I come to this book here, and then we go to group 17, okay, there is something here about the, yes, it is something here. They talked about the melting points. Of course, when we are explaining melting points, we look at the structure and the bonding. You see that? Structure and bonding. When we come back here, they are talking about they become less volatile. Volatility is the ability to vaporize, okay? To vaporize very fast. If something is so volatile then it easily vaporizes. You see that? It easily turns out to be a gas. It turns into a gas easily. That's what it means in simple terms. Now, when we come to this one here, that means we have to look at the forces of attraction that are holding these molecules. The easier you break them, then the more volatile that compound. Now, look at what we are having here. The melting points keep on increasing as you go down the group, okay? So because of that, then that means that the van der Waals forces of attraction in iodine are bigger than these other ones that are up. But now look at the explanation here. Okay, sorry. The explanation here, they are saying the melting points and boiling points of halogens increase down the group. The boiling point data gives us an idea of the volatility of the halogens, i.e., the ease with which they evaporate. Actually, I was talking about melting point, but this is boiling point, okay? Because we are going to turn a liquid into the gas. So we keep on changing what is a solid, then it goes to the liquid, and then from the liquid to the what? To the gas. So all the values are relatively low because they have simple molecular structures, okay? Simple molecular structures. There are only weak van der Waals forces between their diatomic molecules. These forces increase as the number of electrons in the molecules increases with increasing atomic number. The greater the number of electrons, the greater the opportunities for instantaneous dipoles arising within molecules and for induced dipoles to be produced on neighboring molecules. So that's why we say ID, instantaneous dipoles, then induced dipoles, okay? So the larger the molecules, the smaller the van der Waals forces, okay? No. The stronger the van der Waals forces between the molecules, making iodine the least volatile. You see this? The least volatile, and fluorine the most volatile of the halogens we are considering. Now, when we go back to what we are having in the question, volatility will decrease as you descend group 17, okay? So our answer has to be question 18. Compound M is a white solid. It is a chloride of a period 3 element. Information about some reactions starting with compound M is given in this table. And they are saying compound M plus a nonpolar solvent, then you get a colorless solution. And then compound M, then added a little at a time to water, then you get steamer fumes. Q, this is actually the steamer fumes, we know that is HCl, okay? Then a colorless solution. Then fumes of Q are tested with moist blue litmus paper. Then this one turns red. Of course, this one has to be what? Q has to be an acid because it is the one that turns blue litmus to red. You see that? Then solution R plus a few drops of sodium hydroxide, and then excess. We add sodium hydroxide in excess. First of all, here we get a white precipitate, okay? And then it dissolves to give a colorless solution. Actually, when you look at all of this, we have phosphorus pentachloride. Phosphorus pentachloride, when I add it to water, I'm going to get, let's get this phosphorus pentachloride, then plus water, we are going to get phosphoric acid, not so? So H3, then PO4, then plus 5HCl. So these are the steamer white fumes here. So this one produces them. And is this one balanced? Hydrogen is 8. These were 5 plus the 3. Then that means I have to put a 4 here. Then 4 for oxygen and also here. Okay. Then this one will give us that reaction. But when you get magnesium chloride and you add it to water, it just dissolves. Okay. This one just dissolves, and also this one just dissolves. They don't give us the what? The white fumes. So I'll put off B and D. Okay. Then I remain with aluminium chloride. Now aluminium, we have aluminium, then phosphorus and silicon, which hydrolyze when we add them to what? To water. So it is reaction with water. So this one here is actually dimer. Okay, without water of crystallization, I mean without water, this one exists as a dimer. You see that? As a dimer. So we have a 6 here. So that means when we add to water, okay, when you add to water, you are going to get now HCl given off, and then also aluminium in there breaks down. Actually, let me show you from the book. When you check in group 17 here, not group 17, pardon me, there it is periodicity, which is chapter 10 here. So periodicity, we look at the chlorides of period 3 elements. So what happens in here? This is oxides, and then chlorides, where are they? Chlorides of period 3 elements. When it comes to sodium, at the start, the ionic chlorides of sodium and magnesium, what do? For them, they do not react with water. The polar water molecules are attracted to the ions, dissolving the chlorides by breaking down the giant ionic structures. So the solutions formed contain the positive metal ions and the negative chloride ions surrounded by water molecules. The metal ions and the chloride ions are called hydrated ions. So these ones just dissolve, okay? And you are not going to result, this one is not going to result into an acidic or alkaline mixture. You see that? Then aluminium chloride is sometimes represented as this, which suggests that its chemical bonding is likely to be ionic, because this is a metal reacting with a non-metal, not so. So we have aluminium ions and then the chloride ions in the giant lattice. In solid hydrated aluminium chloride crystals, this is the case. However, without water, it exists as a dimer. This can be thought of as a dimer of aluminium chloride. Two molecules are joined together. This is covalently bonded. This one is because of the strong, we call it the high charge density. So it has a bigger charge, but then a smaller what? A smaller volume. So that one will cause the water molecules in there to do what? To lose the water molecules. I mean to lose a hydrogen ion, like I said before. Now, in here, what is going? This is the dimer. Now, there is something they are saying here. They're saying that once we add water, the dimers are broken down and the aluminium ions and chloride ions enter the solution. Each relatively small and highly charged aluminium ion is hydrated and causes a water molecule bonded to it to lose a hydrogen ion, thus turning the solution acidic. So here, one water molecule loses a hydrogen ion, and then we have an OH here, which is negatively charged. Then it will reduce this charge here now to a +2. You see that? This one actually continues until this charge is actually done away with. So you will have 3 OHs here. That is at the end, like I said before in one of the numbers. Okay. Then the non-metal chlorides, this silicon tetrachloride and then phosphorus trichloride are hydrolyzed in water, releasing white fumes of hydrogen chloride in a rapid reaction. You see, because this one was wrong. So silicon tetrafluoride, silicon 4 chloride, that one is a white precipitate. It doesn't dissolve in water. Now, phosphorus pentachloride, this is what I gave you. The white fumes, you have seen them. Now, the white fumes which would have been produced with aluminium chloride actually dissolve in water to give you a more acidic what? Solution. So here we are getting those white fumes, but then they dissolve to give you the acidic solution. Okay. Now, when we add a few drops of sodium hydroxide, we are going to get the white precipitate. That white precipitate is this one here. You are having aluminium. Let me decrease the. We have aluminium here. You are adding it to sodium hydroxide. You are going to get aluminium hydroxide. Okay. That is the white precipitate you're going to see there. Now, when you add more hydroxide, so remember, what is going to happen here is that this one, the white precipitate, is now going to dissolve, and then you form what we call sodium aluminate. Sodium what? Aluminate. So this is the one they are saying dissolves to give a colorless what? Solution. So that means our answer has to be aluminium what? Chloride. You see? Not this phosphorus here. Question 19. Which statement about strontium and its compounds is correct? Now we are looking at a hydroxide, sulfate, nitrate, like that. Okay. Now, as you go down the group, when we check, but they are referring to barium also, magnesium, then calcium. Let's look at that group. Actually, we have magnesium up here, then we have calcium, then we have strontium, and then we have barium. Then we are talking about hydroxides here. Hydroxides of group 2, the solubility of hydroxides of group 2 increases down the group. Okay, now here they are saying strontium hydroxide is more soluble than barium hydroxide. Barium appears to be below strontium, so it is more soluble compared to strontium. So that means we are going to put off A. Then we go to the next one here. Strontium sulfate is more soluble than magnesium sulfate. Now for sulfates, the solubility of sulfates of group 2 decreases down the group. That means magnesium sulfate is more soluble compared to strontium sulfate. And we actually use this confirmatory test. If we want to see that there are barium ions in a solution, we introduce a sulfate into that solution. You will see a white precipitate, which is barium what? Sulfate. So it is less soluble there. So that means magnesium sulfate here is much more soluble compared to strontium sulfate. So this one will go off. Then here they are saying strontium nitrate has a lower thermostability than calcium nitrate. We know that going down the group, thermostability of group 2 nitrates or carbonates increases. Okay, that means strontium nitrate is thermally stable compared to calcium nitrate. In other words, this one requires much more heat to break it down. So if something is thermally stable, you will need much more heat to break it down. So this one can easily break down. Okay, so that means even this one is off. So our answer has to be D, where they are saying strontium is a stronger reducing agent than magnesium. Yes, when you look at all of these ones here, now this one is going to have a smaller atomic radius, but then strontium is going to have a bigger one. So the distance here, let me actually try to make it a little bit bigger. The distance between the nucleus here and the bonding electrons here, the outermost shell electrons, is way bigger. So if this is R2 and maybe this is R1, so R2 is bigger than R1. Okay, so the distance here is way bigger. Metals react by losing electrons. Okay, so since the distance here is bigger, we are going to have, there are more shells here. So there is increased shielding as you go down the group. So because of this increased shielding, the shielding is repulsion between these electrons. Okay, so in there, this implies that these electrons here that are outside here are far from the nucleus. Are we there? So because they are far from the nucleus, that means the nuclear attraction is going to be weak. Yes, the nuclear charge is stronger because nuclear charge depends on the number of protons. As you go down the group, you are adding a shell of electrons and the same number of protons in the nucleus. So the nuclear charge increases, but the nuclear attraction is going to reduce because of this big distance here. Okay, so it becomes very easy for strontium or barium to lose electrons, and therefore they become much more reactive. Okay, so they become much more reactive compared to these ones here. Okay, now because they are much more reactive and they react by losing electrons, now to lose electrons you get oxidized. That means because you are oxidized, then you are a reducing agent. A reducing agent is the one that donates electrons. It is the one that gives electrons. So therefore strontium is a stronger reducing agent compared to magnesium. You see that? All right. Question 20. Sodium bromide is warmed with concentrated sulfuric acid. Which row describes the change in the oxidation number of sulfur and the row of bromide ions in the reaction? Now what happens, we have two types of reactions. So we have sodium bromide here reacting with concentrated sulfuric acid here. Then the first reaction is an acid-base reaction. So we shall get sodium hydrogen sulfate. So the sulfuric acid here loses a proton to the sodium. Okay, so we get sodium hydrogen, to the bromide here, and then you get hydrogen bromide. But because bond angles of these halides here, hydrogen halides, decreases down the group, so this one here actually, in presence of more sulfuric acid, then we are going to see it break down. So we are going to get bromine, then we get sulfur dioxide, and we also get what? Water. Okay, maybe to balance this, we shall need to put a 2 here for bromine, and then hydrogen is 2, and 2, that will be a 4, so I'll put a 2. Oxygen then becomes 2 plus 2, that's a 4, and also this one here. Okay, then from here we can look at, they are talking about the oxidation number of sulfur. Sulfur here we have 2 times 1 for hydrogen, then N, and then oxygen is 4. Each oxygen atom has oxidation number what? -2, so is equal to 0. Then our N becomes, this is a 2 minus 8, that will be -6. So when it crosses the equal signs, it becomes a +6. And then here we have N, then plus 2, then times -2 is equal to 0. Then oxygen, the oxidation number here becomes a +4. Now it decreases from 6 to 4. That means here there is a reduction. Okay, there is a reduction because it decreases, the oxidation number decreases from 4 to 6. And then we look for 6 to 4. Then row of bromide ions. Bromide here, we can see that the oxidation state is a -1, and then the oxidation state here is a what? Is a 0. So that means what is here? There is increase in oxidation state, so this is oxidation. So because bromide ions have been oxidized, then therefore they are reducing agents. So you see that? So our answer is therefore supposed to be B. So reducing agent. As simple as that.